So I just want to do a sound check. Can people on Zoom hear me?
Yes, we can hear
Yes.
you.
Yes? Okay, good. All right, so what I'd like to do first is kind of look at the schedule and sort of make sure that we're on board in terms of what's happening in the next couple weeks. All right, so currently we are in week number 9, okay? And just move this up. And so today, what I'm going to do is I'll probably cover volumes. So we'll be done with the material week number 9 today. And so the midterm 2 will cover everything before 3.3. Okay. And then for the rest of week 9, what I'll do is I will work on the material for week 10. And what this will do is it will clear up some room so that I can have a review on Wednesday. Okay, so remember, this next week is a short week. Okay, so what I'd like to aim for is I'd like to aim for a review on the 28th and on the 2nd. Okay, I'll write these things down in the notes too. And then the midterms will actually be on the 4th and on the 6th. Okay. Any questions on this?
Since it'll be before 3.
Yeah, before 3.3. Okay, so we'll be done with the material today. And then the rest of the week, none of this stuff is covered up. Okay, good. All right, so let me write things down in the notes a little bit more carefully here. Okay, so I'll escape this. Okay, so here are the notes for today. Okay, so first of all, there'll be review for midterm 2. Okay, so we'll run it sort of in the same way that we've done before. So the first review will probably be sort of a general review, which will cover some of the first part of the class. Okay, and then the next review will probably cover more of the portion from the first midterm to the second midterm. So, so the reviews will be on the 28th and on Monday, 11/2. Okay, so this is the Wednesday before fall break, and then the Monday after fall break. So this is Wednesday, and this is Monday. Okay, and again, I'll sort of do things the same way I did before. I'll cover certain topics, and then I'll leave some time for you to actually ask questions on these topics or on any sort of problems that you have involving the topics that are covered on the review. Okay. Now, for midterm 2, we're going to reverse the order just to be fair. So the Bulldogs will come in first. So the Bulldogs will take the midterm on Wednesday, the 4th, so the day after the election, okay? And then the Georgias will take it on Friday. Okay, so that's Friday. All right, again, the format will be kind of the same, 5 problems, 20 points each. You could bring a calculator if you'd like, and it will be closed book on this exam. Okay, any questions on the procedure? Yes, no? All right, so another thing is I will actually send a message out like I did last time about the details of this. So you should receive an email about this. So I'll just say this. We'll send out an email about this. Okay. Good. All right, so today I'd like to start out by reviewing Kramer's rule and also reviewing the formula for computing inverses using cofactors. So let's review Kramer's rule. So let A, B, and N by N matrix. And consider the system of equations AX equals B. Okay. Now, we know that if A is invertible, then this has a unique solution. So we can ask ourselves, can we actually give the solution in terms of certain determinants? And so the answer is yes. So this is Kramer's rule. Okay. So let A be an invertible N by N matrix. Okay. So the solution of AX equals B is given by X equals X1, X2 up to X to the N, where each Xi, so the way we can calculate each Xi is we can take a quotient of the determinants. So the determinant of AIB over the determinant of A. Okay, so we know how to calculate the determinant of A. And what is AIB? AIB is the matrix obtained by just replacing the ith row or ith column of A by B. Because you take out the ith column of A and then you just put in B instead. Okay, hang on, let me clean this up a little bit. Oops, made it worse. Okay, that's better. Okay. All right, so this is Kramer's rule, and we actually did an example of this, and you'll have some examples to do in your homework too. All right. Now, we also have the formula for A inverse. Okay. And so we can do this as follows. So let's say A is invertible. Then this is 1 over the determinant of A. And then you just take the cofactors and then you transpose. So this is C11, C21, CN1, C12, dot, 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 C1N, and this is CNN. And the CIJs are the cofactors that we've defined before. And another way we can write this is the cofactor matrix is called the adjunction matrix, and then we could just divide by the determinant. Like that. Okay, any questions on this, on these statements? All right, now what I'd like to do is I didn't actually have time to really finish the example last time. So I'd like to actually complete the example from last time. And I think it'll just give us good practice in terms of doing, matrix computations. Okay, so this is the example from last time. And let's see, so can calculate the inverse of the following matrix. Okay, so it was a 3 by 3 matrix, 0, -2, -1, 3, 0, 0, -1, 1, 1. Let's call this matrix A. Okay, so we want to calculate the inverse of this. All right. So what I'm going to do is I'm going to label the cofactors. So let's look at C11, for example. So what's that going to be? So that's going to be equal to, I'll just write everything out. It's the A11 entry up here. Yeah. So it's 0 to the 1 plus 1, right? Times the determinant of 0, 0, 1, 1. Okay. And the determinant of this is just 0. Okay. So let's just go down. So we'll have to transpose the matrix later on, but let's just go along the top row. Okay. So what's C12? Well, it's -1 to the 1 plus 2. That's going to be -1 cubed. So we get a -1. And what's the determinant here that we get? Well, we're going to cross out the first row and the second column. So I get 3, 0, -1, 1. Okay. And so when we calculate that determinant, we get -3. All right, everybody with me so far? Yeah.
Well, should
Alright.
that be a -2 in front of the cofactor?
No, we don't. Sorry, can you speak up, please?
Sorry, for C12, how did you get the -1 in front?
Because, sorry, it should be negative. Let's see. I guess it should be. Yeah, it should be a -2, which should be a +2, right? Yeah. C12. Oh, that's interesting. Sorry, what? Yeah. Right. Right. So it should be a 2. I'm sorry about that. You're right. Yeah. So I should be careful here. So maybe I should erase this one first. So the formula. Let me just be very careful again. Okay. Yeah. Okay. So it's -1 times this, and then we have to do the coefficient, right? Okay, so I have to put the coefficient in front of this. So I have to multiply by -2. Actually, is that actually true? No. No, it's just the matrix. You don't have a coefficient in front, right? Yes? What's the formula for cofactor? Well, let's review the formula for the cofactor so that we don't all get confused, right? So let's just do this. So let's write out the formula for the cofactor. So Cij is equal to -1 to the I plus j times the determinant of Aij. Okay, so everyone check that formula. Is that correct or not?
Yeah.
So we don't put the coefficient in front. Okay. All right. So let me get this right then. So we don't put the coefficient in front here, and we don't put the coefficient in front here. And maybe I should be a little bit more careful, and I'll just put a 1 plus. Sorry. I put a 1 plus a 2 here. Okay? All right. Everybody okay with this now? Yes? Yes? Okay, good. All right, so let's continue on. So C13, that's minus 1 to the 4th. And then I'm going to take the determinant of 3, 0, minus 1, 1. Okay, so I'm going to take the first row and then the third column and sort of delete that, and I get this thing. All right, so what do I get? I get 3. All right, everybody okay with that so far? Okay, so what I'll do is I'll just go a little bit faster now, right? Okay, hopefully without making any mistakes. So C21, that's minus 1 because 2 plus 1 is 3, so that's odd. Okay, so I'm going to take out, I'm going to go here, I'm going to take out the second row in the first column. So I get minus 2, minus 1, 1, 1. Okay, so what do I get? I get minus 1, and the determinant is minus 2, minus a minus 1, so that's plus 1 right there. Okay, so minus 1 times minus 1 is 1. Okay. Okay, let's do C22. Okay, so it's minus 1 to the 4th. And then we'll just take out these. So it's 0, minus 1, minus 1, 1. Okay. So what do I get? I get 1 and I get negative 1. Okay, so next one, C23. I have minus 1 because minus 1 to the 5th is minus 1. And then what do? We take this one over here and we take out the second row and third column. So I get 0, minus 2, minus 1, 1. Okay, so I have minus 1 times 2 with a negative. Okay, so I get plus 2. All right, everyone okay with the second row expansions here? Yes. All right. Okay, let's continue on. So 3, 1, 0, minus 1 to the 4th. Okay, so let's see, what do we get? We get, we take out this one and that one, so I get minus 2, minus 1, 0, 0. And the determinant there is 0. C32. So 3, 2, I'm down right here. So I'm taking out the third row in the second column. So it's minus 1. And let's see, third row, second column, 0, minus 1, and 3, 0. Okay. So I get minus 1 and I get minus 3. Okay, and then finally C33, I get minus 1 to the 6th. And then I'm down in the last spot over there. I get 0, minus 2, minus 1, 1. And so the final answer is I get a 2, so that's negative. Oh, sorry, let me make sure, is that right? I have a 3 down. Sorry, let me make sure. 0, minus 2, 3, 0. Sorry. Now let me just erase this. Okay. That's better. Okay, so then I get minus 1 to the 6th, which is 1. And then I get minus 6, I negate that, so that's a 6. So okay, any questions on these computations here? As I said, the cofactor method of calculating inverses is slower than doing Gaussian elimination. Okay. All right. Now we just have to calculate the determinant of A. So what we'll do is we'll just go down the diagonals like we did before. So if I go down this diagonal, I get 0, I get 0 here, and I get -3. Okay, so those are all the diagonals going down from left to right. And then if I go from right to left, what do I get? I get 0 here, I get 0 there, I get -6, so negative or -6. Okay, so that's going to be 6 minus 3, which is 3. Okay, we're in good shape now. Now we can actually just calculate the inverse here. So A inverse is 1/3. Now, I have to transpose this matrix, right? Yeah, so I have to kind of, so the columns become the rows, and the rows become the columns. So the rows are 0, 1, 0, and then what? -3, -1, -3, and finally 3, 2, and a 6. Okay. All right, are there questions on this? How we did this?
Did you do the like the direct? Did you do the determinant A or did you
Yeah, I
do-
did.
Okay.
I went down the diagonals from left to right, and those give me positive things, right? And then when I go from right to left, I get negatives. Okay. I noticed that there are lots of zeros in this, right? Because I had 0, 0, 1, that's going to be 0. -2, 0, -1, that's 0. And I get -1, 3 times 1, that's going to be -3. Okay. And then you just do it the other way.
Could you
Good.
say one more time where the powers for the cofactors come from again?
It's from the definition. It's from this definition right here.
Okay,
You just sum the I and the J together.
okay.
Okay.
Thanks.
Okay, other questions?
Yeah, in the definition of the inverse, what's that it's 1/the determinant times the matrix of the cofactors
Yeah.
equals, and then what is that, adjacent A over determinant
Yeah,
A? Or?
it's a junction matrix.
Oh, gotcha.
The junction matrix is just the matrix of the C's. the
Gotcha.
cofactors. Okay.
Thank you.
Just another way to say it. I think it's in your book too. So. Okay, other questions? All right, so now I'm going to proceed on the geometric interpretation of the determinant. Okay, so uh, 2 by 2 and 3 by 3 determinants. Okay. All right, so here's the idea. So suppose I take, so this is my origin here. Let's say it's 0, 0. And I have a point out here, let's call this AC. And I have another point out here, and this is BD. Okay. Now, if I look at the matrix A, B, C, D. So let's look at this matrix A, B, C, D. And then, I could take its determinant. So the determinant of A is AD minus BC. Okay. Let me just write determinant in here, just to make things a little bit more clear. Okay, so now what I can do is I can sort of draw a parallelogram like this. Oops. And I could look at the parallelogram span by these vectors. And I could look at the area inside of this. And it turns out that the determinant calculates the area of this parallelogram. So in absolute value. Okay, so let me just state that. Okay, so here's the statement. So the area of the parallelogram is the absolute value of the determinant of A. Of course, area has to be positive. Determinants could be like positive or negative. So you have to take the absolute value. Okay, let me just. Okay. Now, if you're in 3 dimensions, oh, and also notice that if the vectors are in the same span, okay, so if they're on the same line, then the volume is, there's no area, right? And so if you have 2 vectors which are linearly dependent, then we know the determinant is equal to 0. Okay, so this makes sense in some ways. All right. Now, what you can do is you can generalize this to something which is like 3-dimensional. So let me just do it this way. So here's 0, 0, 0 over here. Okay. And I could take a vector which kind of goes out here. I don't know, let me call it, let me see, how do I want to label this? Let me just do it this way. So what is A going to be? A11, A12, A13, A21, A22, A33, A31, A32, A33. This is the 2, 3 here. And this is the 3, 3 down on the bottom. Okay. So now let's say that the vertices are at the points given by the columns of the matrix. So I have like A11 here, A21, A31. Okay, so that's one of my vectors. I have another vector which is given by A12, A22, A32. And then I have another vector here which is given by A13, A23, A33. So I have these 3 vectors, and what I can form is I can form what's called a parallelepiped. Okay, so I don't know if I drew this so well, but you can kind of see that. Let me just draw it better. All right, so let's see. Let me just draw it like this, maybe. Okay, so you have something like this, and then you have another parallelogram over here, and then you have another box which looks like that. Okay, so it's kind of like a slanted box, all right? A box which is kind of slanted. And so the volume of this parallelepiped is, of course, equal to the determinant of that. All right, so let me state it more clearly, and we'll do an example in a second. So here's the theorem. If A is a 2x2 matrix, then the area of the parallelogram defined by the columns of A equals the absolute value of the determinant of A. Okay, so that's just the picture that I drew at the beginning of it. Okay. Okay, so now if A is a 3x3 matrix, the volume of the, okay, so parallel, there's only two L's. Oh, piped. Okay, so it's a parallelogram on the bottom, a parallelogram on top, and could be slanted a little bit. Defined by the columns of A is equal to the determinant in absolute value. Okay, any questions on this idea? All right, so now let me give you, let's do an example. Okay, so find the volume of the parallelepiped with vertices at, because I have the origin 1, 4, 0, -2, -5, 2, and finally -1, 2, -1. Okay. So what we have to do, there are various ways we can actually do this problem. But let me kind of draw you a picture, maybe not a totally accurate picture, but just a picture, and I think that'll kind of give you an idea of how to solve this problem. So let's say I have a point at the origin over here, and the first point over here is like, let's say it's 1, 4, 0. And another point here is -2, -5, 2. Okay, so I'm just going to draw a line over here to each of these. And then I can get a parallelogram. Okay. And then the last point that we want is maybe the point up here, -1, 2, -1. Okay. Now, if we want to look at the parallelepiped sort of spanned by this, we get this sort of thing which looks like a box over here. Right? So what we need to do is we need to actually figure out what or how to construct our matrix. So what should we do to construct our matrix? Anyone? How do we get this? So we need some 3x3 matrix. So how do we get this matrix?
You just put like all the vertices and matrix A, it doesn't matter the order.
Well, we have four vertices.
You don't use the 0.
Okay.
Or you said it equals the 0?
Well, what are you really doing there? I actually drew something in, which might give you a hint. What vectors do we use?
-1, 2, -1, 1, 4, 0, -2, -5, 2.
Right, so that's what we're going to use. And so let me just kind of draw pictorially here for you. Okay. That's correct. Oops. Why won't this change color? There we go. All right, so what we're gonna do is we're gonna think of that as being a vector, right? So to get the vector, we have to subtract off 1, 4, 0, and 0, 0, 0. And then similarly, we're gonna use that vector too. Okay, again, it's -2, -5, 2, and then we subtract off 0, 0, 0. Okay, and then finally, we want to use that vector there. Okay, so those three vectors sort of define the parallelepiped. Right? Okay, so now let's construct our A here. Okay, so A is going to be, the first one is -1, 2, -1. The second one is 1, 4, and 0. And the third one's -2, -5, and 2. Okay. Now, 0, 0, 0 could have been any points you want, right? So I could add 4 points, and then you just get the vectors by subtracting off differences of the points, right? So there's nothing that makes 0, 0, 0 special. Okay, good. All right, so this is our matrix. Any question on how we got this matrix? All right, so now let's calculate the determinant. So I don't know. We can use cofactors, or we can use the way to go down diagonal. Any preferences? Cofactors. All right, so let's use cofactors. So if I take the determinant of A, so which row or column should we maybe consider going to?
Row 3.
Okay, row 3, right? All right, so what do? So we take cofactors, so -1, right? And what's the entry here? It's 1, it's 3, 1, right?
Yes.
Okay. Okay, so then, and then you have to put now you have to put the coefficient, right? So then -1 times the determinant of 1, -2, 4, -5. Okay, is that all right? Okay. All right, so now, then we get 0 for the next one. And then the last one, we're going to get -1 to the 3 plus 3. And then I have to put the coefficient in here. And then I have to take -1, 1, 2, and 4.
So we get these coefficients.
It's sorry, let me just write this in. Okay, so we're using the expansion along this row over here. Okay, so the first coefficient is -1, the second coefficient 0, the third coefficient is a 2. Okay, and then we have to worry about the sign and then use the minus. We're just, it's the coefficient plus the cofactor times the cofactor. All right. Okay, so let's do this. All right, so what do we get? All right, so the first one we're going to get is -1 times what?
3.
Okay, so -5, okay, plus 8. Good. Okay, and this last one is 2 times, yeah, it's -4, -2. Very good. All right, so I get -3, and then I get -6 times 2 is -12. So I get -15. Okay, so that's what the determinant is. All right, so what is the volume? Okay, so volume is the absolute value of the determinant of A which is the absolute value of minus 15. And as you said, it's 15. Okay. All right, any questions on how we did this? Yes. No? Okay, so that concludes the section on determinants. So what I'll do for the remainder of the time is start to introduce the concept of an eigenvalue. Okay, so the next thing we're going to talk about, and we'll discuss this more on Wednesday, are eigenvectors and eigenvalues. All right. So let me start with the definition. So let A be an n by n matrix. Okay. So a non-zero vector x such that A times x is a multiple of x for some lambda is called an eigenvector of A. Okay? And lambda is called an eigenvalue of A. All right, so geometrically, what does this look like? Well, let's say I just look at the R2 here. And if I take my x over here, what A does is A just fixes this vector and just, well, it doesn't fix it, but it actually just sends it to the two points on the same line. So if x is an eigenvector, this happens if and only if the line spanned by x is fixed by the linear transformation A. Okay, so if you take any multiple of x, it sends it back into multiples of x. Okay, so in some ways, the picture you should have is you should think about all these, vectors whose span is actually fixed by x. That's what an eigenvector is. All right. Now, so let's do an example. So the question is the vector x equals 1, 4, and eigenvector of the transformation -3, 1, -3, 8. Okay, so is this an eigenvector? Well, what do we have to do to check? Well, we have to check this condition over here. So if I take A times x, it better be a multiple of x, right? All right, so let's do that. So A times x is equal to -3, 1, -3, 8, applied to 1, 4. Okay, so we just do matrix multiplication. And so what do we get? We get -3 plus 4. That's going to be 1. And -3 plus 32, that's going to be 29. Okay. All right, so is this an eigenvector for this matrix A?
No.
No. So this is not equal to lambda times 1, 4. Right, it's not a multiple of 1, 4. So it's not an eigenvector. So hence 1, 4 is not an eigenvector for A. Okay. All right. So, so this kind of begs the question. I mean, we can sort of test a bunch of vectors, and we can actually see whether it's an eigenvector or not an eigenvector. But we like a more systematic way to actually compute eigenvectors and eigenvalues. So we want a systematic method to compute one, eigenvalues of A, and two, eigenvectors of A. All right. Okay, so what I'm going to do next time is actually show you, and it's not very hard. I mean, we can use just methods that we've sort of thought about before to actually figure out what the eigenvalues of A are, of matrix A, and also how to actually compute the eigenvectors once you find the eigenvalues. So the procedure will be find the eigenvalues of A first, and then once you have an eigenvalue, you can compute the eigenvectors using Gaussian elimination. Okay, so this will involve two things. It'll involve solving for roots of a polynomial, which I'll define next time for you. And then two is to use Gaussian elimination. To find null spaces. And we know how to do that, okay? And once we actually set things up, then it's just a procedure to actually do this. Okay, let me stop here. Any questions? Questions from Zoom audience? Okay, great. So we'll stop here and we'll see you on Wednesday.
Thank you.